All right, let's finish this up with number 6. Now, this is going to be a tricky one, so you want to strap in and try to get your critical thinking brain working here. What I want to point out before we get started is that in the problems that we've completed so far, for however many elements we have in a particular problem, we're trying to figure out the empirical formula. Here they're giving us 3. We're used to being given either 3 percentages that that add up to 100%, or just 3 gram values. Okay, this many grams of this element, this many grams of this element, and this many grams of this element. Because that's what you need in order to start your determination of empirical formula. That is true. Here, we're not given all of that information at first. We're given information that we can use to figure out those things. Okay, and obviously, I wouldn't ask you an impossible question. Okay, all the questions I give you are designed to be thought out. So you're going to have to think this one out. Because, as you can see, we've only been given 1 percentage, and that's due to sodium. Okay, so we know what sodium's percent is. That's 25.42%. We do not know what chlorine's percent is, nor do we know oxygen's chlorine percentage. But realize that because all 3 of these percentages have to add up to 100, we only need one or the other. So if we can determine the percent of one of these 2, we can figure out the other. The rest of the problem goes on to say there's a 3.25 gram sample. And in that 3.25 gram sample, there are 4.33 times 10 to the 22nd atoms of oxygen. That's the information we need. So what we're going to do here is we're gonna do a little bit of a process. There's gonna be a little bit of a process. So we're gonna go from atoms of oxygen. We're gonna use Avogadro's number to convert to moles of oxygen. Then we'll use the molar mass to convert to grams of oxygen. Now that we have grams of oxygen, we can set up a calculation in which we divide however many grams of oxygen we have by the total sample. And what's that going to give us? That's going to give us the percent oxygen. And we can use this percent oxygen to help us determine the percent chlorine. So here we go. I'm going to start with 4.33 times 10 to the 22nd atoms of oxygen. I'm going to convert out of that by using Avogadro's number. Which is per 1 mole of oxygen. And then I'm going to go from moles of oxygen into grams of oxygen. So atoms of oxygen will cancel, moles of oxygen will cancel. So I'll be left with grams of oxygen. So, like I always stress, please don't try to do these scientific notation problems in your calculator. You're really prone to mistakes, and you can really miss some of the big points here. You're really missing out on learning opportunities. I suggest that you deal with the M values and the N values separately. So deal with the front of the scientific notation first, then deal with the exponents. And it's going to look something like this. When you do your calculator work and you understand that you need to have 3 significant figures, you're going to have 11.5 after you punch that in your calculator. Then, by looking at the times 10 with the exponent second, I get to simplify what I'm doing here. So I have a times 10 to the 22nd divided by times 10 to the 23rd. And if you remember what we do when we divide exponents, we subtract them. So that ends up being -1. So this is times 10 to the -1 grams of oxygen. But this isn't improper scientific notation because this is more than 10. So because this has gotten too large to be in scientific notation, I'm going to move that decimal 1 place to the left, and I am going to make the exponent 1 larger because this value has gotten too large. That's going to be times 10 to the 0, which is the same thing as 1.15 grams of oxygen. Well, that is the value that I'm going to plug in and then divide by 3.25 because that's the total mass of the sample. Turn on 1.15 divided by 3.25. That ends up being 35, and I'll go 3 significant figures here, 35.4%. So we get 35.4%. And when we go to subtract 25.42 and 35.4 from 100, we get 39.18% for chlorine. Now I have the 3 percentages I need to continue my empirical formula problem. So I'm going to take these, assume a 100-gram sample, and I'll have 25.42 grams of sodium. And I'll let you guys know I've actually already worked this out and solved this problem once on a video, only to realize that I copied this down incorrectly, and I wrote down N, as in nitrogen, and I converted this incorrectly, and it made the whole problem come out wacky. So this is actually the second time I've recorded this. So I'm going to convert this. Let's see, sodium. What is your mass? 22.990. 22.990 grams of sodium is in 1 mole of sodium. There are my crosshairs. Grams of sodium is going to cancel out. So that's going to be 25.42 divided by 22.990. That's going to be 1.1, 4 significant figures, 0.6 moles of sodium. Let's do the same thing with chlorine. So 39.18 grams of chlorine. 35.45 grams of chlorine are in 1 mole of chlorine. Grams will cancel. Let's see, calculation. 1.8 divided by 35.45 and 4 significant figures. We're coming out to essentially the exact same thing for chlorine. And then I have one more. It's going to be the 35.4 grams of oxygen, 15.999 grams of oxygen in 1 mole of oxygen. Ooh, goodness. Calculation time, 35.4 divided by 15.999. And we get, 3 sigma figures, 2.21 moles of oxygen. Now I'm going to divide all of these by the smallest value, which is 1.015, 1.105. Now these are going to come out to be 1. I know that easily enough. This divided by 1.105, even without using the calculator, I can tell that is 2. And so I'm going to have an empirical formula, 1 sodium, 1 chlorine, and 2 oxygens. And so my empirical formula is going to be NaClO2.